Hello, I'm Professor Von Schmohawk, and welcome to YU. In the previous lectures, we explored some examples of the earliest number systems which were used primarily for counting objects. These counting numbers are called natural numbers. The natural numbers start at 1 and can count to arbitrarily large quantities. As we have seen, Roman numerals are one of many possible ways to represent natural numbers. The Roman system was eventually replaced with the modern decimal number system, which uses positional notation and only 10 numeric symbols. The decimal number system was found to be superior to the ancient Roman system because of the simple rules it uses to create numbers. In the decimal system, there are 10 numeric symbols, 0 through 9, called digits. Depending on the column they occupy, these digits represent the quantity of ones, tens, hundreds, thousands, and so on, which make up the number. In positional notation, the column occupied by a digit determines the multiplier for that digit. For example, in the decimal system, the value of the rightmost digit is multiplied by 1. The digit in the next column to the left is multiplied by 10. The next digit is multiplied by 100, and so on. The value of a number is the sum of all its digits times their multipliers. For example, the value of the decimal number 1879 is 1 times 1000 plus 8 times 100 plus 7 times 10 plus 9 times 1. In any positional notation, each column's multiplier differs from the adjacent column by a constant multiple called the base of the number system. In the decimal system, each column multiplier is 10 times the previous column. Therefore, the decimal system is called a base 10 number system. There are an infinite number of columns in the decimal number system, with each column multiplier being 10 times bigger than the column to the right. However, when writing a number, the zeros in front are normally not written. We can count up to 9 using only the ones column. Once we've reached 9, the ones column starts over at 0 and the tens column increments. As we continue counting, the tens column counts the number of times that the ones column has passed from 9 to 0. In other words, the tens column registers the number of tens which we have counted. This continues until we reach 99. At that point, the ones and tens column start over at 0 and the hundreds column increments. The positional notation system is simple. Every time a column passes from 9 to 0, the next column to the left increments. How is it that we ended up with a number system based on multiples of 10? There is not any good reason for choosing 10 over some other number, other than the fact that people have 10 fingers and probably originally communicated quantities using their fingers. But what if we were cartoon characters with 4 digits on each hand? Is it possible that in cartoon land, everyone uses a number system based on multiples of 8 instead of 10? How would a base 8 or octal number system work? In octal, there are only 8 numeric symbols instead of 10 as in decimal. Instead of 0 through 9, the symbols 0 through 7 are used. The symbols 8 and 9 are not needed. Counting in octal is very similar to counting in decimal. Since there are no symbols for 8 or 9, the highest quantity which can be represented in the ones column is 7. Counting an eighth item causes the ones column to start over at 0 and the next column to increment. So the second column counts the number of eighths. Therefore, in octal, the number following 7 is 10, which looks just like the decimal number 10. After octal 10 comes octal 11, 12, and so on until we get to octal 17. At that point, we go to octal 20. The second column has now counted 2 eighths, or 16. We continue like this until we get to the highest number we can represent with 2 digits, octal 77. At that point, the ones and eighths column start over at 0, and the third column increments. The 1 in the third column represents 8 eighths, or 64. Each column multiplier is 8 times the previous one. Every number which can be written in decimal can also be written in octal, although after counting to 7, the way the quantities are represented is completely different. It is easy to convert an octal number to decimal when you consider how positional notation works. Let's take, for example, the octal number 1750. As in decimal, the value of the octal number is the sum of all its digits times their multipliers. So the number 1750 represents 1 times 512 plus 7 times 64 plus 5 times 8 plus 0 ones, which adds up to the quantity which in decimal is called 1000. You may sometimes see a small subscript 8 or 10 after an octal or decimal number, in case there may be some confusion about which base is being used. Digital computers use electronic circuits called flip-flops to represent numbers. Each flip-flop can store a single bit which can represent either a 0 or a 1. Multiple bits can be combined to represent a base 2 or binary number. In the binary number system, 0 and 1 are the only two numeric symbols. Since binary is base 2, each column multiplier is 2 times the multiplier of the previous digit. And just like decimal or octal numbers, the value of a binary number is the sum of all its digits times their multipliers. Since the digits are either 1 or 0, the calculation is simple. We just add the multipliers of all the columns which contain ones. For example, the binary number 11010 represents 116 plus 18 plus 12, which is equal to 26. Even though digital computers store numbers in binary, it can be quite tedious to write down or remember large binary numbers. For instance, the number 1,000,000 in binary is
1111010110110100000.
Early in the history of digital computers, engineers found that it was easier to use octal notation than to deal with long strings of ones and zeros. 3 binary digits can be represented by a single octal symbol. It is easy to memorize the 8 possible combinations of 3 binary bits. To convert a multiple-digit octal number to binary, each octal digit in the number is converted to a 3-bit binary equivalent, and the binary digits are all combined into a single binary number. Any leading zeros can be removed. To convert a binary number to octal, we do the same thing in reverse. To convert this binary number back to octal, we split it into 3-bit groups starting from the right. And each 3-bit group is then converted to its equivalent octal symbol. So the octal equivalent to this binary number is 3654660. A lot easier to remember than all those ones and zeros. Today, computer storage is normally organized into 8-bit groups called bytes. Because of this, many computer engineers prefer to use base 16, otherwise known as hexadecimal or hex, instead of octal. With hexadecimal, every group of 4 bits converts to a single hex symbol. 2 hex symbols represent exactly 1 byte. Even fewer digits than octal are required to represent a given number, and it's just as easy to convert back and forth to binary. Hexadecimal numbers use 16 numeric symbols. The symbols 0 through 9 are used just as in decimal, but 6 more symbols are needed. Instead of making up new symbols, the letters A through F are used to represent what we call 10 through 15 in decimal. Counting in hexadecimal works the same way as in decimal or octal, except that hex uses 16 symbols per digit. Because each column multiplier is 16 times larger than the previous column, hexadecimal can represent large numbers with fewer digits than octal or decimal. When counting in hexadecimal, after getting to F, which is decimal 15, we go to 10, which is decimal 16, then 11, 12, and so on. Once we reach 1F, we go to 20, which is decimal 32. When we get to the largest number which we can represent with 2 hex digits, FF, we go to 100, which is decimal 256, and so on. As we mentioned, using the hex notation, 4 binary bits can be represented by a single hex symbol. Each of the 16 possible combinations of 4 bits is equivalent to a single hex digit. Let's convert the same binary number as before to hex. Starting from the right, we group the digits into groups of 4. Each group of binary digits is then converted to its equivalent hex symbol. So we have seen how the same natural number can be represented in base 2 using 2 numeric symbols, base 8 using 8 symbols, base 10 using 10 symbols, and base 16 using 16 symbols. But no matter how we choose to write this natural number, it still represents the same quantity. As you have seen, we use the same basic rules for counting in binary, octal, decimal, and hexadecimal. The only difference is that each base has a different number of numeric symbols. So using positional notation, we can create a number system using any natural base we like. Try creating one of your own. Who knows, it might catch on.